Hello all. This video describes you the basic concept of differential equations. If we want to solve an engineering problem, normally engineering problems arise from different physical situations, right? So whenever you take a certain physical situation, that physical situation leads to an engineering problem. And see, when you have such an engineering problem, we first have to formulate the problem as a mathematical expression in terms of variables, functions, and equations, right? Such an expression is actually known as a mathematical model of the given problem, right? The process of setting up this model, solving it mathematically, and interpreting the result in physical or other terms is actually called mathematical modeling, or sometimes we briefly call it as modeling. Modeling needs experience, which we shall gain by discussing various examples and problems, right? And see, many physical concepts, when you take them, like velocity or acceleration, they're all simply derivatives, correct? Right? When you take whether velocity or acceleration, they are simply derivatives. So when you consider a particular model, it is very often an equation containing derivatives of unknown functions. Such a model is actually called a differential equation, right? So when you consider any physical situation and when you model it mathematically, it leads to a differential equation, and it involves different kinds of derivatives of unknown functions, right? So when we discuss a differential equation, it is normally of two kinds. One is ordinary differential equation and the second one is a partial differential equation. Particularly, when you are given, for example, if you are given a function of only one variable, let us say you are given u as a function of x. When you are given u as a function of x, you can easily differentiate u with respect to x completely. Whereas, for example, if you are given u as a function of two different variables x and y, when you are given it this way, now since it is a function of two variables, you can evaluate derivative of u with respect to x or with respect to y, but now this is partially, right? You cannot completely differentiate u with respect to x or y. That's how you see, depending on the number of variables, right? Depending on particularly the number of independent variables. When you have exactly one independent variable in the given differential equation, we take such a differential equation as ordinary differential equation. And see, by chance, if you have more number of independent variables in the given differential equation, then we take such a differential equation as partial differential equation. Right? See, for example, for a function of this kind, I can write one differential equation of this way: du by dx plus some u is equal to e to the power of x. Look at it. This is a differential equation because it consists of one derivative of u with respect to x. And here you can see u is the dependent variable and x is the independent variable. As you have exactly one dependent variable and one independent variable, I can take this as an ordinary differential equation. Whereas coming to this, if I write a differential equation of this kind, dou u by dou x plus dou u by dou y is equal to some sine x, let us say. Right now, if you take a differential equation of this kind, you can observe u is the dependent variable, but the independent variables are two, x as well as y. So since you have two independent variables, right? Since you have two independent variables, I'm calling this differential equation as a partial differential equation, right? So in simple, differential equations are of two types: ordinary differential equations and partial differential equations, right? When you have exactly one dependent variable and one independent variable, we simply call it as an ordinary differential equation. When you have more number of either dependent variables or independent variables, then you can call it as a partial differential equation. But see, in our discussion, we are going to concentrate only on ordinary differential equations. As you can see here, an ordinary differential equation is an equation that contains one or several derivatives of an unknown function, which we usually call y of x. As I told you just before, you have only one dependent variable y and one independent variable, either x or t sometimes, right? So when your equation involves only derivatives of that dependent variable with respect to that independent variable, right? Something like, you may have either dy by dx or even either higher derivatives of, this dependent variable. You may have dy by dx or even higher derivatives like d square y by dx square in the given differential equation. When you have the derivatives of only one unknown function and with respect to one independent variable, we call such a differential equation as an ordinary differential equation, right? So look at this example. Right, now look at this. See, I gave you three examples here. If you look at the first one, it is y dash is equals to cos x. When it is y prime, as you know, the notation, we can write y prime as simply dy by dx. And see, it is equals to cos x. When dy by dx is equal to cos x is a differential equation, you can understand y is the only dependent variable and x is the only independent variable. So since it has exactly one dependent and one independent variable, and moreover, there is exactly one derivative of this dependent variable. So it is clearly an ordinary differential equation. And even if you look at this, the second one, see, it has again one dependent variable y and one independent variable x, right? But this time it has a second order derivative. Second order means d square y by dx square plus 9y is equals to e to the power of minus 2x. When you have a second order derivative, right, no problem. Even it is also a derivative because it has the derivative of one dependent variable with respect to one independent variable. Again, we can call this as also what you call an ordinary differential equation, right? Coming to this, right? If you look at these terms, y prime or y triple prime, when it is y prime, it is dy by dx. And when it is y triple prime, it is actually d cube y by dx cube, right? Even here it is y prime again. So dy by dx. So in all the three terms, there are three different derivatives here, right? Here it is y prime whole square, right? Even if you take this as a different term, you have totally three different terms. In either of the three terms, you can see there is exactly one dependent variable and one independent variable. That's how all these examples are ordinary differential equations, right? So you can just identify a differential equation as an ordinary differential equation when that equation has derivatives of only one dependent variable with respect to one independent variable, right? So that's how you can just identify that. And then particularly look at this. If you take this first differential equation, y prime is equal to cos x, and even as you know, we can rewrite it as dy by dx is equal to cos x, correct? So when it is dy by dx is equal to cos x, you can look at this derivative. It has exactly the first order derivative, correct? So when this has first order derivative, we can take the order of this differential equation as 1, right? When it comes to the second differential equation, it has what you call, d square by dx square in this equation, which is a second order derivative, isn't it? So since it has a second order derivative, we can take the order of this differential equation as 2. And when it comes to the third, it has now two different derivatives. One is y prime and the second one is y triple prime, correct? So when it has this way, we'll see the highest ordered derivative involved in that. So when the highest order derivative involved here in this is 3, third order derivative, we can take the order of that differential equation as what you call 3, right? So as we know here, as you understood, an ODE is said to be of order n if the nth derivative of the unknown function is the highest derivative of y in the equation. So looking at the differential equation, we need to identify which is the highest ordered derivative available in the given differential equation, right? Identify which is the highest ordered derivative, right, in the given differential equation. Then order of that highest ordered derivative is order of the differential equation, right? Order of highest ordered derivative is the order of the differential equation, right? Now see, if you look at these three differential equations, uh, the first one is a first order differential equation, second one is a second order differential equation, and the third is a third order differential equation. And this concept of order gives us a useful classification into ODEs of first order, second order, and so on, right? But see, though there are different types of ordinary differential different orders of ordinary differential equation, in our discussion will be completely on only first order ordinary differential equations for now, right? So what is a first order ordinary differential equation? You understood now. When it is a first order ordinary differential equation, right? See, first of all, it is an equation, so there must be an equality, and it is a differential equation, so there must be a derivative, and that too, you are considering only ordinary differential equations. So that's how you can expect. You must have derivatives of this kind, and moreover, it is a first order ordinary differential equation. So when it is a first order ordinary differential equation, you must expect only a first order derivative, right? So this is equal to some function of x comma y. So this is, a one form of first order ordinary differential equation. Though it is not mentioned here, we are considering first order, first degree ordinary differential equations. Okay, right? Then uh, the most general form, right? What a first order ordinary differential equation may be, right? See, as you can see here, these first order ordinary differential equations contain only the first derivative y dash or else dy by dx, and may contain y and any given functions of x, right? So it may contain one derivative y prime and some function of either x or y. Okay, and then see, the most general form of any first order ordinary differential equation is this. It contains, as you understood here, it contains an independent variable x and then a dependent variable y, and then the derivative of this dependent variable y prime, right? So now, because it is an equation, I'm equating all this to 0. Okay, so this is the most general form. And then in some cases, it may also be written in this way: y prime is equals to f of x comma y, as I told you. And normally we call this kind of expression as an explicit form. Or else, the other one is, this equation 4. We can take this as the implicit form of what you call first order ordinary differential equation. Then see, when we define an ordinary differential equation, we must have a target. We are just defining what are all these. When we define an ordinary differential equation, when we consider a first order ordinary differential equation, our target is to find out its solution, right? So what is a solution actually? If you just recall these things, if you are given one equation of this kind, let us say 2x plus 3 is equals to 0. See, when it is 2x plus 3 is equal to 0, we call this as an algebraic equation. And then the solution of this equation is this: x is equals to minus 3 by 2. We take x is equal to minus 3 by 2 as the solution because this x definitely satisfies the given equation. Because x satisfies this equation, we take it as the solution. In a similar way, when you are given a differential equation of first order, something like this: dy by dx is equals to f of x comma y, right? Then what do you mean by solution of this differential equation here? Understand, solution in the sense finding the value of unknown, correct? Finding the value of, or else the value of unknown which satisfies the given equation, right? Very much similar to this algebraic equation. Here also, we need to see which is the unknown. Understand, when we write dy by dx, there must be some function, which can be written something like this: y is equal to some function of x, right? You are differentiating y with respect to x. It means already you had one function y, which is a function of x, correct? So when you have a function of this kind, understand, x is the input and y is the output, as you know, isn't it? So already x is known to you. You choose it yourselves. Corresponding to one change in x here, there will be an equivalent change in y, correct? So y is depending on x. So x is already known to you, but y is unknown, right? So keeping this simple view in, keeping this simple idea in view, you can just understand, in dy by dx is equal to f of x comma y, in this differential equation, the unknown is y, right? In fact, in any differential equation, whatever the dependent variable you have, right, similar to this y, whatever the dependent variable you have, that is what your unknown, right? So solving this differential equation, in the sense finding this unknown, in the sense we need to find out the value of this dependent variable as a function of independent variable. So solving this differential equation means finding the value of this dependent variable, right? Look at it this way. If you are given one function, let us say h of x, you can call this function h of x as the solution of this differential equation, right? As I told you, solution. You can take y is equal to h of x as the solution of given differential equation capital F of x y dash. See, you take this as a solution when h of x is particularly defined and differentiable and is such that the given the equation becomes an identity when we substitute both y and y dash, right, in the given differential equation. Understand, when y is h of x, y prime is nothing but h prime of x, right, the derivative of h, as these two are equal. Now see, in the given differential equation, if you substitute y and y dash by h and h dash, and if this equation is satisfied, then you can call h of x as the solution of this differential equation. Understand, h of x is the solution of this differential equation when this h of x satisfies the given differential equation, right? That's the way. And then understand, our target is to find out such a solution, right? You are given a differential equation, then the target is to find out this solution. Then, as you know, there are so many methods to solve those differential equations, right? Now, in our next video, we'll just discuss what are all those methods one by one, right? Thanks for watching this. See you in the next video. Hello all. In our last video, we discussed about the introduction to differential equations, and we even discussed about the solution of differential equations. And in this video, let me just give you the first method of finding solution of any first order ordinary differential equation, right? As you can expect, we cannot find solutions of every differential equation with variable separable method, but there are certain constraints. Let us see this. Then see, as we considered in the last class, in the last video, you are given now, let us consider a first order ordinary differential equation of this kind. Dy by dx is equals to f of x comma y. Now see, when you are given a differential equation of this kind, we are trying to find out its solution. In the sense, we are trying to find out this dependent variable in terms of independent variable. Understand it this way. Look at this right hand side function. If this function can be written as a product of two individual functions in which one is a function of x and the other one is a function of y, right? I repeat, when you are given a function of two variables f of x comma y, if you can write this as a product of two different functions in which one is a function of x and the other one is a function of y, then only we can use variable separable method to solve these kind of differential equations, right? Understand, if this is possible, and see what we can do next to this. Dy by dx is equal to, now you have a product of these two functions. Now, when you can rewrite the given equation in this way, from now we'll just separate the variables. What are the variables here? X and y. By separating the variables, we'll try to write all functions of x on one side and then the other functions of y on the other side. So you see, as you have dy in the numerator here, I'm just bringing the functions of y to the left hand side. So we can write it this way: 1 by g2 of y into dy is equals to, already here is a g1 of x, I'm writing it as it is. Then see, if you can take dx to the other side, it becomes dx. Now see, like this, you can easily separate the variables on either sides of this equality, right? Now you have all functions of y on the left hand side and all functions of x on the right hand side. This is what separation of variables. Now, after separating these variables, the next step is only to integrate this, these expressions on both sides. Now, whatever the answer you get after this integration, that is going to be the solution of given differential equation, right? Remember, this solution may not be explicit always, right? We may get some implicit form of the solution, but we should not worry about that. Right now, let me just take one simple example here to understand this. Let us say this is the differential equation you are given. Dy by dx is equals to y by x. Now see, when this is the differential equation, look at it this way. I'm just trying to separate the variables. One thing is clear here. On the right hand side, we can write it as y multiplied by 1 by x. Now see, this function, the right hand side function, it can be written as a product of two different functions. One is a function of x and the other is a function of y. As we can rewrite it this way, we can use what you call variable separable method, right? And see, I'm just trying to separate the variables. because you have dy in the numerator here, I'm bringing all functions of y to the left hand side. So it becomes something like 1 by y into dy is equals to, already here is a 1 by x, and then I'm sending dx to the other side, so it is dx. Next, we need to just integrate this on both sides, right? So then we'll get it like this, integration of 1 by y dy, 1 by y dy is equals to 1 by x, integration of 1 by x dx. Now this implies, when it is integration of 1 by y, we can write its integration as log y is equals to integration of 1 by x is log x. And see, when we integrate, because it's a definite integral, we need to always add an integrating constant, and I'm writing it as log c. Now if you can further simplify this, you can see log y is equals to, it's just like log a plus log b. And log a plus log b is log ab, correct? So we can write it as log cx. Now see, from this step, I'm just taking exponential on both sides. So when we take exponential on both sides, we'll get the answer finally as y is equal to cx, right? You can just cross check if you want. This expression definitely satisfies the given differential equation. That's how we can call this as the solution of this differential equation. And this is the procedure to find out the solution using what you call variable separable method, right? So keeping this in view, let's now take a few problems. Look at this problem, the first one. Solve y prime is equals to e power 3x minus 2y plus x square into e power minus 2y. I'm just writing this, given equation once again, dy by dx is equals to, and see, we need to first observe whether we can apply variable separable method or not. So for that, I'm just rewriting this equation on the right hand side. Look at the first term. You have e power 3x minus 2y, but I'm writing it as e power 3x multiplied by e to the power of minus 2y. Then plus, this x square times e to the power of minus 2y. Then now, if you look at these terms on the right hand side carefully, we can take e power minus 2y common from both the terms. So that we'll get it this way, e power 3x plus x square into e to the power of minus 2y. Now, see, when you observe these two functions together, one is a function of x and other is a function of y, and you see they're in product. So since they are in product and individually they are functions of two different variables, we can use what you call variable separable method. I'm just extending this idea because again, you see, you have dy in the numerator here. I'm bringing all functions of y to the left hand side. So it becomes 1 by e to the power of minus 2y into dy is equals to, I'm just writing all this function as it is, e power 3x plus x square into dx. And see, now we need to just take integration on both sides. And see here on the left hand side, while taking the integration, you have e power minus 2y in the denominator. So you can easily take this to the numerator. And when it goes to the numerator, it becomes e to the power of plus 2y. dy is equals to, and this I'm writing it as it is, e power 3x plus x square into dx. Now see this, when you integrate e power 2y, it becomes e to the power of 2y by 2 is equals to, when you integrate this, it is e to the power of 3x by 3 plus, even when you integrate x square, it is x cubed by 3. And obviously we can add what you call an integrating constant c, right? Like this, we can easily solve a differential equation of this kind. Now let me take one more problem. Now see, if you take this one, 3 into e power x tan y plus 1 minus e power x into secant square y. I don't know particularly whether we can use variable separable method or not, but I'll try to see whether I can separate the variables or not. So to observe that, see what I'm doing. I'm just writing the first term as it is, in this equation, you have exactly two different terms. This is the first one and this is the second one. See, I'm writing the first term as it is, 3 e power x into tan y dx. And see, now I'm sending the second term to the other side. So it becomes minus 1 minus e power x into secant square y dy. Right? Now see, I'm just trying to observe the other things as well. If you look at these two terms individually on the left hand side, everything is in product. Right? And here also, 1 minus e power x is one single term, and this is multiplied with secant square y. Again, they are also in product. So it looks like we can easily separate the variables. We can bring all functions of x on one side and other functions, functions of y onto the right hand side. That's quite easy now. Let's just do that. See what I'm doing here. I'm keeping, because you see, we have a dx here on the left hand side. Because I have dx, I'm keeping functions of x here itself, 3 e power x, and also I'm bringing this 1 minus e power x to the left hand side. So it becomes 1 minus e power x is equals to, I'm just writing minus here itself for time being, and then what you have here, secant square y divided by, you're bringing this tan y to the other side. So it comes to the denominator here, tan y dy. Next thing, we need to just integrate this on both sides. Look at this. I'm just writing this 3 is a constant, I'm writing it aside. And then what happens here? E power x divided by 1 minus e to the power of x is equals to, I'm writing this minus aside. Then it is integration of secant square y divided by tan y. Right? Now, see, we need to just integrate this on both sides. Now, see, we need to integrate this on both sides. Look at these terms little carefully. Look at the right-hand side term. You have tan y in the denominator and its differentiation is secant square y. So it is just like integration of some derivative f dash divided by f. When f is in the denominator, its derivative is there in the numerator. So when you have these kind of expressions, integration of this expression is log f. Correct? Now see, can we use this idea in both the integrals? I mean on both the sides. Look at it this way. You have there actually 1 minus e power x in the denominator. So when we differentiate this, differentiation of 1 is 0 and this minus has to be carried as it is. And when we differentiate e power x, it is again e power x. So when you have minus e power x by 1 minus e power x in the numerator, integration of this expression will be log of 1 minus e power x. Correct? But if you look at this, 1 minus sign is missing in the numerator. Correct? But see here also on the right hand side, there is an extra minus. So instead of keeping this on the right hand side, let me just write it on the left hand side, we can just shift it quite easily so that, both the problems will be solved easily. Right? I'm just trying to do that here. While writing this integral sign, instead of writing minus sign here on the right side, I'm writing it here. Right now, so that it becomes plus here. Now, when everything is all right, we can just use this integration of f dash by f formula. When you use this, see what happens, then it implies 3 into, it is just exactly as f dash by f now. So when it is integration of f dash by f, as we know, it is log of f is in the denominator, 1 minus e power x is equals to, the same thing here also you see, it's like f dash by f. So that it is log of tan y plus, obviously, we take one integrating constant, it is, let us say, log c. So then it is equals to, as we know, when you have a log x, we can easily write this as log x power a, right? Using this idea, I'm writing it this way, log 1 minus e power x whole to the power of 3. And it is equals to, you see on the right hand side, it is like log a plus log b. So we can write it as log of c tan y. Correct? Now see, we have both log functions on either sides. So I can take again exponential on both sides. So when I take exponential, we'll get these things. 1 minus e power x whole to the power of 3 is equals to c times tan y. Right? So like this, we can solve, this problem using what you call variable separable method. Then let me also explain you this problem. Now see, when it is xy square plus x into dx plus yx square plus y into dy is equals to 0. Now look at this. I'm just trying to separate the variables again. In what way we can do this, you see? From the first term, we can take x common. You see, we have x common in both the terms. So when you take x common from them, you will get x into y square plus 1 dx. And see, I'm also simultaneously sending this term to the other side. So it is equals to minus, when you take y common from this, see what you get? Y into x square plus 1 dy. Right? Now see, when you look at these terms individually, we can observe, they are all in product. So since they are in product, they can be easily separated. Right? So I'm just separating the variables here. This implies, see here you have dx in the numerator, right? On the left hand side. Because you have dx here, I'm just writing all functions of x on the left hand side. So let me just keep this x as it is, as in this. And see here it is x square plus 1 on the right hand side. I'm just bringing that x square plus 1 to left hand side. So it comes in the denominator x square plus 1 dx. It is equals to this minus, I'm writing it as it is, and then here it is a y, and if you can bring this y square plus 1 to the right side, it becomes y square plus 1 dy, right? And then see, we got, exact separation of variables very clearly. Now see, I'm just trying to integrate this on both sides. So integration of, I'm just writing this as it is, x by x square plus 1 dx is equals to, I'm writing this minus as it is, integration of y divided by y square plus 1 dy, right? See, again, I remember this formula. When it is integration of f prime by f, its integration is log f, isn't it? I still remember this formula. Look at it, look at this left hand side now. You have x square plus 1 in the denominator now. So in case if you take this as f, what would be its derivative? It should be 2x. And even the same thing on the right hand side, you should have what you call 2y in the numerator. So when you have this expression, its integration will be, log of x square plus 1. Right? Because this 2 is missing here, you can just multiply with a 2 in both the terms on either sides. Right? Because you are multiplying on either sides, no need to worry, you will get that the same thing. Now see, looking at now these terms on either sides, you can observe clearly they are like f by f prime. So therefore, when you integrate them on the left hand side, you first get log of x square plus 1. It is equals to, I'm writing this minus as it is, then log of y square plus 1 is equal to, I'm just adding an integrating constant like log c. So then it implies, I can write it like this, log of x square plus 1 is equal to, see this right hand side. It is just like log of log c minus log b, or else log a minus log b. So that you can write as log of a by b, which is c divided by y square plus 1. Now see again, if you take exponential on both sides, see what you get here, x square plus 1 is equals to c divided by y square plus 1. So if you want it more particularly, you can just multiply with y square plus 1 on both sides. So that, we'll get this x square plus 1 into y square plus 1 is equals to c. So like this, you can solve easily any problem using variable separable method. But understand, you can use variable separable method only when we can separate these variables. Now, look at this question also, right? In a very similar way, if you look at this, let's see again, if you look at the differential equation quite clearly, here it is a function of y and this is a function of x, they are in product. Here also the same thing, right? They are in product. So since everything is in product, you can easily separate the variables. See how we can separate them. See, I'm just writing all this differential equation. Again, it is 1 plus e to the power of y into cos x dx is equals to, I'm just sending this term to the other side. So it becomes minus e to the power of y into sin x dy. Then see, again, the same idea. Because you have dx on the left hand side, I'm bringing all functions of x to this side. So already here is a cos x. Then when you bring sin x to the left hand side, it becomes sin x dx is equals to, I'm writing this minus as it is. Then here you have e power y divided by, if you can bring 1 plus e power y to this side, 1 plus e to the power of y come in the denominator and dy. Right? Now see, from here, we are just going to take integration. Now, therefore, it becomes integration of cos x divided by sin x dx is equals to minus, I'm writing it as it is, integration of e power y divided by 1 plus e power y dy. Now, this is equals to, it's just like, again, same story, right? F prime by f, right? On the left hand side, you can see it is just like f prime by f. So that its integration is log f, like log sin x. And it is equal to, you can write this minus sign as it is. What about this you see now? It is again the same way. If you take this denominator as f, its derivative is there in the numerator. So even if when you integrate this, you'll get this as log of 1 plus e power y plus, obviously you can take one integrating constant, because these two are logarithmic functions. I'm taking this as also log c. Now see if you can simplify this. See what happens. Log sin x is equals to What happens to this? It's like log a minus log b, right? So it is log of c divided by 1 plus e power y. Now, if you take again exponential on both sides, we'll get this as sin x is equals to c divided by 1 plus e power y. And if you want to still simplify this, you can just write it this way: 1 plus e power y into sin x is equals to c. So like this, you can solve first order ordinary differential equations using variable separable method, right? Let us see about linear ordinary differential equations of first order. Right, let me first define what is a linear first order ordinary differential equation. Remember, linear in the sense the degree is 1, right? In fact, we had seen differential equations of this kind: dy by dx is equals to f of x comma y, in general. But particularly, when you are given a differential equations of this kind, we call it as a linear. If a differential equation is of this kind, dy by dx is equals to, look at this, when we write dy by dx, y is the dependent variable and x is the independent variable, correct? So, if you are given a differential equation of this kind, dy by dx plus some function of x multiplied by this dependent variable y is equals to, some function of x on the right hand side. Earlier, in the last method, we had seen this as, on the right hand side, only a function of two different variables. You may have any function of two variables on the right hand side. But now, particularly, we are not expecting a function of this kind. But see, you have a function of x multiplied by different variable, and on the right hand side, exclusively, it is a function of only x. Okay, maybe some constants may be included in this, but not the dependent variable. All right. Now see, when you have this kind of expression, this kind of differential equation, we call this as a linear differential equation in y. See, this is a linear differential equation in y. See, you are calling it as in y because the dependent variable is y. And moreover, you see, this is linear because, anywhere in this differential equation, the degree of dependent variable or its derivatives is 1, right? See, degree in the sense, look at the powers of y or powers of dy by dx. Or, if you have, anyway, we are not discussing the higher order derivatives, but even if you extend this, in a case when you have a differential equation of second order, even if you take the power of this derivative, in a differential equation, if you have higher powers of either y or its derivatives, I mean the dependent variable or its derivatives, right? Then it is a non-linear. When you don't have either powers of y or powers of its derivative, when you have only powers of y or powers of derivative as 1, we call it as a linear differential equation of this dependent variable y, right? And see, in some cases, in some of the differential equation, you may have, this kind of terms. The dependent variable may be multiplied by its corresponding derivative. Even in this case, we consider the degree of this term as more than 1. So even if the differential equation has products of dependent variable and its derivatives, we cannot take it as a linear differential equation. So in any term individually, when you consider a differential equation, in any term, the degree of dependent variable or its derivatives, even when the dependent variable and its derivative are together, in either the case, the degree must be exactly 1. Then only we call them as what you call linear differential equations. And if the dependent variable is y, we take it as a linear differential equation in y. In a similar way, understand it, let it be like this. You may be given x as a function of y, right? Normally we consider y as a function of x, correct? In this case, as we know, y is the dependent variable and x is the independent variable. But see, when you are given a function of this kind, x as a function of y, may not be f every time, let it be something like g. When x is given as a function of y, you can then understand x is the dependent variable, but y as the independent variable in this case. So when you have this kind of equation, as we know, we can evaluate dx by dy because x is the dependent variable this time, correct? So we can evaluate dx by dy. Then in that case, the derivatives may be something like this, dx by dy. So one is this, linear differential equation in y. If not that, You may be given a differential equation of this kind, dx by dy plus, when the dependent variable is x, here you may get one function of y multiplied by this dependent variable x, and it is equals to some function of this independent variable y. Right? Now, in case if you have a differential equation of this kind, then we are calling this as a linear differential equation in this dependent variable x. Right? When the dependent variable is y, we are calling it as a linear differential equation in y, and when the dependent variable is x, it is a linear differential equation in x. Right? In either case, we now need to find out the solution. Okay? Now see, the idea is to find out the solution of this differential equation, maybe a differential equation in y or a differential equation in x. Now see, for example, if I take this first one, dy by dx is equals to, dy by dx plus p of x into y is equals to q of x. Let me take the linear differential equation in y. Now see, I'm just giving you the working rule on how to find the solution of this kind of differential equation. Remember, whatever the coefficient you'll be given for this y, that is p of x. Right? While we are solving the problems, we need to see what is the coefficient of this y on the left hand side. And see, whatever the coefficient you have here, that is p of x. And whatever the function of x you have on the right hand side, that is q of x. Keeping that in view, see, I'm just giving you the working rule. We need to first find out what you call the integrating factor. Right? Integrating factor helps us to find out the solution quite easily. Integrating factor is e to the power of, now see, you have already identified what is p of x. Then the integrating factor is e to the power of integration of p of x dx. Right? So you'll get some expression here. I'm just abbreviating it as if. Right? This is to understand we got what you call integrating factor. Now see, after getting this integrating factor, we'll just write the solution like this. Then the solution of this linear differential equation is, see, what is the dependent variable here? It is y, dependent variable multiplied by this integrating factor is equals to integration of q of x into this integrating factor. Right? And you integrate this with respect to x plus, then you will add some integrating constant c. So when you are given a linear differential equation, the first step is to find out its integrating factor, and it is this, e to the power of integration of p of x dx. And after getting this integrating factor, we just use this idea to find out the solution. Right? So it is dependent variable multiplied by integrating factor is equals to right hand side function multiplied by integrating factor, integration of this product plus some integrating constant c. Right? Very simple. Then in a similar way, when you are given a linear differential equation in x, let us say if it is dx by dy is plus, dx by dy plus dx by dy plus, one function of y multiplied by dependent variable x is equals to another function of y. Now, when it is this, you can understand now the dependent variable is x. So as in the previous case, even in this case, the first step is to find out what you call integrating factor. Now, because what you call dependent variable is x, right? A little change you can observe in finding integrating factor. Now look at the coefficient here. See, the dependent variable is x and its coefficient is now a function of y. Since this is a function of y, while calculating the integrating factor, we just take it this way, e to the power of integration of p of y dy. Right? See, in the previous case, when it was a function of x, we have integrated it with respect to x itself. But now here it is a function of y, look at it. That's how we try to integrate it with respect to y. This results out as a function of y, and see, it is the integrating factor. Now see, after getting this integrating factor, now we are writing the solution. And see how we write the solution. Now, here you see in the previous case, we have written the dependent variable first. In a very similar way, in this case, the dependent variable is x. So the solution is x times integrating factor is equals to integration of, see, the right hand side function multiplied by the integrating factor right? And see here now this product is a function of y. So I'm integrating it with respect to y, plus you will just add an integrating constant c. So with this simple idea, looking at the given differential equation, we need to solve, we need to first identify whether that is a linear differential equation or not, right? So looking at the differential equation, we need to see which method is suitable, and if in case if it is linear differential equation, we can find solution with this simple idea. So let me just take one simple problem to understand how we can solve it when it is a linear differential equation, right? Let's take this question. Solve y prime plus secant x into y is equals to tan x. Look at it this way. When you have a differential equation of this kind, as we discussed till now, dy by dx plus one function of x into y is equal to, other function of x. Now see, we call this as what you call a linear differential equation in x. I'm sorry, linear differential equation in y, correct? Now when you rewrite this differential equation, as we know, y prime can be written as dy by dx plus secant x into y is equals to, tan x, right? See, these two are very much similar to each other, right? So this is a linear differential equation in y for sure. When this is a linear differential equation in y, how we are finding the solution? When you compare these two, before that, I'm just writing these two, what is p of x and q of x. Now see, when you compare these two expressions, it is clear, you can understand p of x is the coefficient of y, so it is secant x. And if you take the right hand side function, what it is, q of x, it is equals to tan x, right? Now keeping this in mind, I'm first finding what you call this integrating factor. So to find out the solution, as this is a linear differential equation, the first step is to find out the integrating factor. So how can you find the integrating factor? In this case, it is e to the power of integration of p of x dx. And so it is equals to, I'm writing here, e to the power of integration of, see how much is p of x is secant x. So it is secant x dx. So then it is equals to, look at it, when it is e to the power of, as we know, integration of secant x is log of secant x plus tan x, right? Log mod secant x plus tan x. Now see, as you can understand from this, there you see what you have here, the last step, e to the power of log of something. When you have e power log or ln, e power ln of x, right? We can write this as simply only x, right? Keeping that simple idea in view, we can write this as modulus of secant x plus tan x, right? So now this is the integrating factor we got. Now see, after getting the integrating factor, we need to now write the solution. Therefore, the solution of given linear ordinary differential equation is, right, see, I'm writing it this way, y into integrating factor is equals to integration of q of x multiplied by integrating factor, and see, this product has to be integrated with respect to x plus some integrating constant c, right? See, now I'm just substituting everything into this. This implies y into, see what, how much is the integrating factor we got? It is secant x plus tan x. I'm just writing it as it is, secant x plus tan x is equals to, I'm writing here, you see, integration of, how much is q of x? It is tan x. So I'm writing tan x as it is. Then if you multiply this with integrating factor is secant x plus tan x. Right, so I'm just writing this constant as it is. Now see, here you are just integrating it with respect to x. So let me just write it again. I'm just writing all the terms again. Here it is q of x tan x multiplied by integrating factor secant x plus tan x. Right, now see how much is this? It is equals to, on the left hand side, it is only y into secant x plus tan x. I'm just writing it as it is. And on the right hand side, you see integration of, I'm just multiplying all this, I mean these two terms with tan x. So it comes out as secant x tan x plus integration of tan square x. And remember, when it is tan square x, we can actually write it as secant square x minus 1. Correct? See, I've just multiplied tan x and secant x, so it is secant x tan x. And then when it is tan x into tan x, it is actually tan square x. But as we know, integration of tan square x doesn't exist, so we can rewrite it as secant square x minus 1, right? Then it is equals to integration of secant x tan x is, as we know, secant x plus for secant square x, the integration is tan x minus 1. I mean, for 1, the integration is x. Plus you can just add an integrating constant c. So therefore the solution is y into secant x plus tan x is equals to secant x plus tan x minus x plus c, right? So like this, looking at the given differential equation, we need to find what you call the solution, right? When it is a differential equation, when it is a linear differential equation, so this is the procedure to find out the solution of that. Right now, looking at this differential equation, let me just try to solve this also. Now see, this is the differential equation. I'm just writing it again for our convenience. 1 plus x square into y prime. As we know, y prime is this, dy by dx plus y is equals to e to the power of tan inverse x. Right? Recall what, when we call one differential equation as linear, if it is of this form, dy by dx plus p of x into y is equals to q of x. Point number one, the coefficient of dy by dx must be 1, correct? But see, when you look at this, dy by dx, it has a coefficient of 1 plus x square. Let us first make the coefficient of this derivative as 1. So let's just divide all these terms with this 1 plus x square. So then we can write it as, when we divide everything by 1 plus x square, we get, the first term as dy by dx plus, here if you divide it, so 1 by 1 plus x square into y is equals to, on the right hand side it is e to the power of tan inverse x by 1 plus x square. Right? Now it is clearly a linear differential equation in y. Right? Look at this. Instead of p of x, we have this, and instead of q of x, we have all this. So looking at that, I'm just writing what are p of x and q of x. Let p of x is equals to, see, it is the coefficient of this dependent variable y. So in this case, it is 1 by 1 plus x square, and then q of x is equal to, all this right hand side function. It is e power tan inverse x divided by 1 plus x square. Right now we got everything. So let us first find integrating factor. So when you calculate the integrating factor, you can just recollect it. It is e to the power of integration of p of x dx. Correct? Then it is equals to e to the power of integration of, I'm just writing it this way, 1 divided by 1 plus x square dx. As we know, integration of 1 by 1 plus x square is tan inverse x, so it becomes e to the power of tan inverse x. And since it is integrating factor, we don't add any kind of integrating constants. Right? So therefore, the integrating factor is this. Now, keeping this in view, if you write the solution, therefore, the solution of given differential equation is, see how much it will be. I'm just writing it this way. Dependent variable is y multiplied by integrating factor. So it is e to the power of tan inverse x is equals to integration of, see how much is the right hand side function, it is e to the power of tan inverse x by 1 plus x square multiplied by, this integrating factor. See how much we got the integrating factor? It is also e to the power of tan inverse x. And we need to integrate this product with respect to x plus some integrating constant c. Now we need to see how best we can solve, this right hand side integral, right? See, there are different ways to solve this integration. You can, if you want, you can take a substitution, right? So I'm just taking that way. If I take tan inverse x is equals to something like, t. When I take tan inverse x is equals to t, if you differentiate this on both sides, as we know, differentiation of tan inverse x is 1 by 1 plus x square dx is equals to dt. Right? So then this implies, this substitution, we are taking it only to evaluate this right hand side integral. So I'm not substituting anything on the left hand side. I'm just writing it as it is. E to the power of tan inverse x is equals to, how can we write this? You see, when you have 1 by 1 plus x square dx, all this becomes only dt. And here it is e to the power of t multiplied by e to the power of t. Because, e power tan inverse x is there. So this is equals to, it is nothing but e power 2t, right? So when we integrate that, we get it as e to the power of 2t by 2, right? So which is nothing but e to the power of 2 tan inverse x by 2, right? So therefore, the solution is, I'm writing the final lines, the solution is y into e to the power of tan inverse x is equals to, now in place of all this integration, we can use this idea, 1 by 2 into e to the power of 2 tan inverse x plus, some integrating constant c. So like this, we can easily solve this differential equation also. Okay. Thanks for watching this video. We'll continue a few more problems, few more methods in coming videos. See you. Right? So when the degree of either dependent variable or its derivatives is more than 1, we normally call it as a non-linear differential equation. And this Bernoulli's differential equation is one special type of non-linear differential equations. Right? So let me just first give you what is a Bernoulli's differential equation, and then we can also discuss its solution procedure. Look at this. Now see this particular form. Look at this differential equation, as you can see here, dy by dx plus p of x into y is equals to q of x into y to the power of n. See, as we discussed in the last class, in the case of linear differential equation, it was this actually, dy by dx plus p of x into y is equals to only q of x. But now this right hand side function is multiplied by this y to the power of n. N may be any integer, remember, right? Now see, when you have this kind of expression on the right hand side, because the power of this dependent variable is not 1, remember, n is definitely more than 1, right? When exactly y power n is there on this right hand side, we are calling this type of differential equation as what you call a Bernoulli differential equation. In fact, you see, when you have y power n here, it is definitely a non-linear differential equation. Right? It is a non-linear differential equation and a particular type. Right? This is not the only non-linear type of differential equation. But when you have y power n of y power n kind of things on the right hand side, we are calling it as what you call a Bernoulli's differential equation. Wait a second again. Right. Now see, this is what a Bernoulli's differential equation, and as you can see from the definition itself, when you have y power n, it's clearly a non-linear differential equation. But see, when you are given a non-linear differential equation, as usually, our target is to find out its solution. But see, we are quite familiar with linear type differential equations, right? So what we are going to do now, when you are given a differential equation of this kind, when it is a Bernoulli's differential equation, we just try to reduce this into what you call a linear differential equation. Okay, so let me just tell you how it is into different cases. We first take case number 1. I'm just thinking of it this way. Though you are given it as y power n, and of course I have considered n is greater than 1. But what if it is n is equals to 1 exactly? See, in case if n is 1, see this right hand side becomes simply q of x into y, as you can see here. The left hand side remains as it is. But see, this right hand side becomes, it is simply q of x into y power 1. But see, when it is only q of x into y on the right hand side, as you know, you have both y's on either sides. You can just bring them to one side. So when you bring q of x to the left hand side, we can take y common from them, and hence, you know, the equation becomes like this. Right? Now, when it is this, you see, we can easily separate the variables. As you know, both p and q are functions of x. So that, you know, all this bracket is also a function of x only. So when it is a function of x, we can easily separate what you call the variables. Right? When we separate the variables, you know, as we did, a few days ago, we can easily solve it also. So when n is 1, there is no issue definitely. But the problem comes when n is more than 1, right? That's how we are calling it as a non-linear differential equation. So what we are going to do, as I told you now, when you are given a non-linear differential equation, we normally try to reduce that into what you call a linear differential equation, right? When you are given a non-linear differential equation, we try to, by some means, you know, you may use different kind of transformations, different, you know, mathematical techniques, but we try to reduce this into a linear type differential equation. As we know, you know, when you have a linear differential equation, we know how to solve this. We have a specific procedure for that, right? So to make use of this simple idea, see, we are proceeding it this way. In case 2, when n is not equals to 1, see, the equation then becomes like this: q of x into y to the power of n on the right hand side. To reduce this into a linear differential equation, the first step, you know, we are multiplying all these terms by y to the power of minus n, right? We are just multiplying all these terms by y to the power of minus n. See, what's the idea here? We don't want to see this y power n on the right hand side. So just to remove that, you are multiplying all the terms by y to the power of minus n. So when you do so, what happens, you see? You will get y power minus n multiplied by dy by dx. So you will get this term. Then p of x into, it is y times y to the power of minus n. So we can just write it as y to the power of 1 minus n, you see. That's how you got this term. Then on the right hand side, already there is a y power n, and now you are multiplying it with y power minus n. So it is y to the power of n minus 1, n minus n, which is y power 0, and it is 1. Since it is 1, you see, I've just written as only q. So in the first step, we have just multiplied all these terms by y to the power of minus n. So we got this equation. But see now, to be a linear differential equation, we should have exactly the dependent variable here, and we should have the coefficient of dy by dx as 1. Right? Both are missing. So to get here exactly a dependent variable, we want only a dependent variable here, nothing else. So to get a dependent variable exactly here, see, I'm just using a transformation. I'm just taking, you know, all this y to the power of 1 minus n as some other variable u, right? Then you can just think of it. When you take y power 1 minus n is equals to u, what happens to, you know, remaining things? See, I'm taking y to the power of 1 minus n is equals to u. Now let me just differentiate this on both sides. So what happens, you know, as we know, differentiation of x power n, it is n x to the power of n minus 1, you know, the same formula I'm using here. So when we differentiate that, we get it these things: 1 minus n into y to the power of, already there is a 1 minus n, and you will again subtract 1 here. 1 minus n minus 1 into dy by dx is equals to, on the right hand side, we get it as du by dx. So let's see what happens here. 1 minus n into y to the power of, see, this 1 can be cancelled here. So we'll get 1 minus y to the power of minus n into dy by dx is equals to, you know, this du by dx. See what you have here actually, if you look at this differential equation, you have actually this term. What it is? Y to the power of minus n into dy by dx. You have y to the power of minus n into dy by dx, and the same you got here also. Right? From which you got this? You know, from this substitution. So if you rewrite this, we can write y to the power of minus n into dy by dx as it is 1 by 1 minus n into du by dx. Right? So now what you are doing now, you see, when you have y power 1 minus n is equals to u, you can write this y power minus n into dy by dx as 1 by 1 minus n into du by dx. That's how you see, I've replaced it this way. In fact, first of all, they have written it this way, 1 minus n into y power minus n into dy by dx. Oh, this is differentiation. Then see, when you substitute everything into this, we get 1 by 1 minus n into du by dx plus, instead of this y to the power of 1 minus n, they have written it as, you see, u is equals to q on the right hand side. Right? Even see, still we didn't get the exact linear form. What is the exact linear form? We should have coefficient of this du by dx as 1. So to get exactly that 1, now I'm just multiplying all these terms by 1 minus n. Right? See what we did? We have just considered one substitution of this kind, and thereby this y to the power of minus n into dy by dx, it can be written as 1 by 1 minus n into dy by du by dx. That's how here you got this 1 by 1 minus n into du by dx plus, instead of this y power 1 minus n, we can write it as u, and then this q remains as it is on the right hand side. Then when we multiply all these terms by 1 minus n, you see, you will get exactly this equation. Right? As we know, this 1 minus n is a constant. So when you multiply this constant by p, all this is a simple function of x only anyway. Right? So it is absolutely, similar to what you call a linear differential equation. And that too, it's a linear differential equation of first order. Right? And see here, the dependent variable is now u. Since the dependent variable is u, I'm taking this as a linear differential equation of first order in u. Right? Now see, this differential equation can be solved very easily, as we did in the previous class. I mean, in the case of linear differential equations. And after getting the solution for the linear differential equation, to get the solution of original differential equation, we replace this u by, y to the power of 1 minus n. Right? So whatever the transformation we considered earlier, we just resubstitute that, to get the solution in terms of y. Right? So this is how simply we try to solve what you call Bernoulli's differential equation. See, whenever you have y to the power of n on the right hand side along with q of x, we particularly take it as a Bernoulli's differential equation. But see, this type of idea, what we did here, we first divided it. Then we considered some kind of substitution. Then we reduce that into a linear differential equation. Right? So this simple procedure can be extended even when you have some other nonlinear functions here on the right hand side. Right? Instead of y to the power of n, even if you have some other nonlinear expressions, maybe it's some trigonometric functions, right? Anything else, maybe sometimes exponential functions. Even in those cases, we can just extend this idea of reducing a nonlinear differential equation into a linear differential equation. Right? Anyway, we'll see few problems of that kind now. If anyone of you have any questions, as I told you, please use chat option. Now let's just look at this question. Look at the question carefully. It is y dash minus y by x is equals to y square by x square. Right? See, I'm just rewriting the given differential equation. Y prime means you can write it as dy by dx minus, I'm just writing it this way, 1 by x into y is equals to, on the right hand side, how can we write this? You see, on the right hand side, is equals to, I'm just writing it this way, 1 by x square multiplied by y square. Right? Look at it. It is clearly a Bernoulli's differential equation. Right? See, when you have a differential equation of this kind, dy by dx plus p of x into y is equals to some function of x into y to the power of n. When you have a differential equation of this kind, we are calling it as a Bernoulli's differential equation, isn't it? Now see, when you compare these two, you can look at this. N is equals to 2. This is a Bernoulli's differential equation. Now to solve this differential equation, we need to reduce that into a linear type differential equation. Okay, let us just try to do that as we discussed till now. To reduce this into a linear differential equation, we need to divide all these terms by y square. The first step is to remove this y square on the right hand side. So either you can divide it by y square, or I can write it this way, multiply all the terms by y to the power of minus 2. Right? Divided by y square or multiplication by y power minus 2, both are same, right? Now this implies, when you multiply all these things by y square, you can see y to the power of minus 2 into dy by dx minus 1 by x into y multiplied by y power minus 2. See how much it is? Y to the power of 1 minus 2, right? Which is y to the power of minus 1 is equals to 1 by x square. See, y square into y power minus 2 is simply 1. Now see, as we discussed till now, we should have what you call coefficient of this as 1, and moreover we should have exactly a dependent variable here. So you don't have a dependent variable, you see. So that to get a dependent variable here, I'll just take this y power minus 1 as some other substitution, some other variable. Let y power minus 1 is equal to some u. Now when I take this substitution, see, if we differentiate this on both sides, differentiation of y power minus 1 is minus 1 into y to the power of minus 1 minus 1. See, it is n into x to the power of n minus 1, the same formula. Then if you differentiate y, it is dy by dx is equals to du by dx. Right? So then this implies, if I simplify this, I'm just first writing this y powers, y to the power of minus 2 into dy by dx. See, exactly this is what you need from this differential equation. You are just trying to replace all these things. So you just need to write it only for this term. So I have written only this, and here is a minus sign, you see. I'm just sending this to the other side, so that we'll get it like this, minus du by dx. Now see, with this substitution, what can we do? If I give some numbers to this, this is equation number 1, and let me take this as equation number 2. Now therefore from equation 2, we can write this y power minus 2 as minus du by dx minus, there is a 1 by x, and this in place of y power minus 1, you can write it as u is equals to, I'm just keeping this 1 by x square as it is. Right? So yeah, we got the dependent variable here, but see, as we expected, we should have what you call 1 as the coefficient for this du by dx. So to get a 1 there, I'm just multiplying all the terms by minus. So then we can rewrite this as du by dx plus 1 by x into u is equals to minus 1 by x square. Correct? Now clearly this is a linear type differential equation, and when you look at these things, we can write it this way: p of x is equals to, the coefficient of dependent variable is p of x, which is 1 by x, and the right hand side function is q of x, it is minus 1 by x square. Now when we identify these things, we can now calculate what you call the integrating factor. So therefore the integrating factor is e to the power of integration of p of x dx. Now see, it is e to the power of integration of 1 by x is p of x, 1 by x dx. And this is equal to e to the power of integration of 1 by x, as we know it is log x. So therefore e power log x means it is only x. Right? So integrating factor is simply x. So therefore, I'm just giving one more number to this, it is 3. Right? Now therefore, the solution of equation 3 is, in equation 3, if you look at this carefully, dependent variable is u. That's how, while writing the solution, we take u multiplied by integrating factor, it is x, is equals to integration of, see, the right hand side function is this, minus 1 by x square multiplied by integrating factor again x, and then we integrate this with respect to x plus some constant c. So therefore, x into u, right? Don't consider this as u of x. This is product. Then see, x into u is equals to, you can cancel 1x here, you see, and this minus I'm writing it as it is. So when you cancel 1x, it remains only 1 by x here. When you integrate that 1 by x, it is log x plus, some constant c. Now this is the solution of what you call equation number 3, but we want the solution of equation 1, So therefore, the solution of equation 1, see, this is, now see, to get the solution of equation 1, we need to replace u in terms of, by some transformation we considered earlier. See, this is the transformation we considered. Now see, I'm just replacing this u by y to the power of minus 1. So it is x y to the power of minus 1 is equals to minus log x plus c. So this is the solution of this differential equation. Right? So if anybody have any questions, you can please raise your hand. I'll just allow you to unmute yourselves. But I hope it's fine. Okay, then let's look at one more question. Right, now look at this. Right, see, as I mentioned, we may not have only powers of y on the right hand side. As I told you, we may have some other expressions instead of y powers. Right, you know, it is such a question here. This is, I cannot say this is exactly a Bernoulli's type differential equation, but this is also a nonlinear differential equation. Right, so even when you are given a nonlinear differential equation, we try to reduce that into a linear type differential equation. So you see, right, so I'm just doing it this way. Now see, when it is y prime, I'm just writing it like this, dy by dx plus 1 by x. See, there is no dependent term here, look at it, is equals to, I'm writing it this way, 1 by x square into e to the power of y. Right, see, if I'm not audible, please tell me immediately. Dy by dx plus 1 by x is equals to 1 by x square into e to the power of y. Then see what happens here. See, the first step is to remove this non-linear term on the right hand side. When it was some power of y, we have divided all these terms by, you know, this power of y. And instead of y powers, you know, now we have an exponential function in y. So to remove this term, let us divide all these terms by e power y. Or else we can write it this way. Multiply all the terms by, see, e to the power of minus y. Right? Division by e power y or multiplication by e power minus y, both are same. Now see, when you multiply all these terms by this, see what happens. If I give this as some equation 1, then equation 1 implies you are multiplying with e power minus y. So it is e power minus y into dy by dx plus, I'm writing this 1 by x as it is, but I'm multiplying this with this e power minus y is equals to 1 by x square into, you know, when you multiply these two, e power y and e power minus y, it is simply a 1. Right, so I'm not doing anything. Now see, it's exactly, not exactly a linear type, but still we need to reduce this. As we discussed in the previous problem, here in place of this, we should have exactly a dependent variable, but you have something else, you know. So to get a dependent variable here, I'm just taking a substitution. See what it is, e to the power of minus y is equals to u. Right, if you take this as u, what happens, you know, if you differentiate this, differentiation of this is, first of all, e to the power of minus y into dy by dx is equals to, see, you will get it this way. I forget one more thing. When you differentiate e power minus y, first it is e power minus y. And along with this, you will also get a minus in the denominator, or else just beside this. Right? You are differentiating this, you know, minus e power minus y into dy by dx is equals to, it is du by dx. But see here what you have only e power minus y into dy by dx, right? We don't want this minus sign on the left hand side. So I'm just writing it this way, e to the power of minus y into dy by dx is equals to minus du by dx. Correct? Now, if I substitute everything, let me take this as some equation number 2. Now, therefore, equation 2 implies, see what happens when we substitute everything into this. In place of this first term, now we can write it as minus du by dx plus 1 by x into, you know, in place of this e power minus y, I'm writing it as u is equals to this 1 by x square. All right. Then see, again, we don't want to get, you know, this negative sign besides this derivative. So I'm just rewriting it again by multiplying everything with minus sign. So we can rewrite it as du by dx minus 1 by x into u is equals to, you know, minus 1 by x square. Right? Now, when you have this, let me first find out the integrating factor. Let me take this as some equation number 3. Now, see if you find out the integrating factor. Integrating factor is e to the power of, see, the p of x is coefficient of this, what you call dependent variable. So it is e to the power of integration of minus 1 by x dx. So this is equals to e to the power of, if you keep this minus sign aside, what remains here is 1 by x. Integration of 1 by x is, you know, log x. Correct? So then it is equals to e to the power of, you can write it like this. You can write this minus sign as a power to x. So it is log x to the power of minus 1. So you can cancel e and log, you know. So we can write this as x power minus 1. Or if you want it more particularly, we can also write this as 1 by x. Right? So clearly, integrating factor is what you call 1 by x. Now, therefore, if you now write the solution of equation 3, solution of equation 3 is, see how much it is. Now, the dependent variable in 3 is u. So, I'm writing u multiplied by the integrating factor 1 by x is equals to integration of, see what is the integrating, I mean, the right hand side function, it is minus 1 by x square into integrating factor 1 by x. And since these two are functions of x, you are multiplying it by x, I mean, you are integrating it with respect to x plus some constant c. Then it is equals to, you can write this minus sign aside, and see here you have 1 by x cube. When it is 1 by x cube, what may be the integration of that? Right? Since, you know, when you have minus 2 by x cube, when you have minus 2 by x cube, its integration is 1 by x square. But as you don't have this 2 here, you know, it comes to the other side. So if it is minus 1 by x cube, its integration is 1 by 2x square. Correct? So I'm just using that idea here. I'm even considering this minus also here. So keeping that also in mind, so when you write its integration, it is simply 1 by x square. Correct? So 1 by x square plus, you know, I'm sorry, 2x square plus some integrating constant c. Now this is actually the solution of equation number 3, but I want the solution of equation number 1. So therefore, to get the equation of, the solution of equation 1, we need to replace u, you know, as a function of y. The solution of equation 1 is, now see, in place of y, see what substitution we considered, this one, e power minus y. I'm substituting that. So it is e to the power of minus y into 1 by x is equals to, see, it is 1 by 2x square plus c. Right? So like this, you can easily find out the solution of even Bernoulli's differential equations. In fact, see, whenever you are given either Bernoulli's differential equation or in general nonlinear differential equations, by, you know, some kind of mathematical ideas, you are reducing that into a linear differential equation. And when it is a linear differential equation, you know how to find its solution. Right? If anybody have any confusion in this, you can just raise your hand. I'll just allow you to speak out. Somebody is asking me to explain this integration. Let me just ask you in this way. See, we have here minus 1 by x cube, right? If you just recall it, when we differentiate 1 by x, it is minus 1 by x square. And when it is 1 by x square, see, when we differentiate 1 by x square, we get it as actually minus 2 by x cube. Right? Now see, when the differentiation of 1 by x square is minus 2x cube, what will be the integration of minus 2x cube? It is 1 by x square, right? The simple antiderivative. So when it is minus 2 by x cube, its integration is 1 by x square. But see, there is no 2, right? So since there is no 2, you can just multiply and divide it by 2. Right? Or otherwise, you can just write this 2 on the other side. In case if it is minus 1 by x cube, the 2 comes to the other side, you know, in the denominator. So in the case of minus 1 by x cube, when we integrate it, it is simply 1 by 2x square. That's what I have written here. Correct? I hope it is all right now. And still, if anything else there, you can ask me. Right? Now, let me just give you one more question. Look at this. Right? Again, this is also not a straight, what you call Bernoulli's differential equation, but still it is a nonlinear type differential equation. See, when it is a nonlinear type differential equation, I'm writing it again, you see here, dy by dx plus x sine 2y is equals to x cube cos square y. Right? Now see, it's clearly a nonlinear differential equation because the dependent variable is clearly y and you have all nonlinear terms involving y. Right? When you have only y or dy by dx, that was okay. But see, when you have sine 2y or cos square y, they're all nonlinear terms. Correct? That's how we need to reduce this first into a linear type differential equation, and from that we can solve it easily. So the first thing as we are doing, look at the right hand side function. Whatever the nonlinear term you have here in this, divide all this equation by this nonlinear term. Okay, let me just do that. See, I cannot write multiply, right? So I'm just dividing it by cos square y. So we get it this way: 1 by cos square y dy by dx plus x into sine 2y divided by cos square y is equals to x cube. Okay. Then this implies when it is 1 by cos, we know it is secant. So when it is 1 by cos square, you can understand it is secant square y dy by dx. Then plus x into, see how I am writing this. When it is sine 2y, we can write it as 2 sine y cos y. That's what you call a trigonometric transformation. In a similar way, I'm writing this cos square y as it is. And this is equals to x cube. And see, I'm writing it again. Secant square y into dy by dx plus x into, see here you can cancel 1 cos y, you see. 1 cos y can be cancelled, so that only sine y by cos y remains. Right? See, I'm writing it this way. Here is a 2, 2x. I'm writing it aside. And then what remains? 1 cos y is cancelled. So remaining is sine y by cos y. So when it is sine y by cos y, we can write it as tan y is equals to x cube. Now see, this is what you got. The term on the right hand side is removed. But see, we got something else other than the dependent variable. So to get a dependent variable here in this place, we need to take one substitution. So let me take tan y is equals to u. Now see, when I take this substitution, when I take tan y is equals to u, if I differentiate this on both sides, differentiation of tan y is secant square y into, if you differentiate y again, it is dy by dx is equals to du by dx. Now see, the same thing is there here in this secant square y. Let me just give some numbers. This is equation 1 and let me take this as equation number 2. If you look at equation 2, the same term is available in the first term here. So now I can replace all this by simply what you call du by dx. Right? I'm just writing here. And then therefore equation 2 implies, see what happens. Now in place of this secant square y dy by dx, I'm writing it as du by dx plus 2x into, in place of tan y, we can write it as u is equals to x cube. Now see, clearly this is a linear differential equation. So when you have a linear differential equation, if I take this as some equation 3, now for corresponding to equation 3, to find out its solution, we need to first find what you call the integrating factor. So the integrating factor is e to the power of integration of 2x dx. Then it is e to the power of integration of, you can just write this 2 aside, you see. I'm just integrating this, keeping 2 aside. Integration of x is x square by 2. So 2 can be cancelled out and the integrating factor is e to the power of x square. Right? Looking typical, but see, integration of integrating factor is e power x square. Then when it is e to the power of x square, then see, let us write the solution. Therefore, the solution of what you call equation 3 is, see, the dependent variable in equation 3 is u. So it is u multiplied by integrating factor e to the power of x square is equals to integration of what it is here, x cube into e to the power of x square dx plus c. Right? Now see, to integrate this right hand side, we need to use some substitution. We cannot directly integrate that. So let us take some substitution. See, I don't want to get this, I don't want to see this e power x square here, right? When it is a simple exponential function, we can easily integrate that, correct? So keeping that idea in view, I'm just writing it this way. Let x square is equals to some t. When I take x square is equals to t, we can write differentiation of this 2x dx is equals to dt. Or else we can write x dx is equals to 1 by 2 into dt. So therefore, u into e to the power of x square, I'm not substituting this on the left hand side. It is equals to integration of, see, we can write this x cube as x square into x. write this x cube as x square into x. So 1x, in place of x square, we can write it as t, but there is one more x, that x into this dx. It is 1 by 2 into dt. And what remains here? It is only this e power x square. So we get it as e to the power of t, right? And then what you call an integrating constant c. Now see, this is equals to, if you keep this 1 by 2 aside, then integration of this. When you have t into e power t, we can use what you call integration by parts. So I'm keeping t as it is. Then when we integrate e power t, it is e to the power of t minus, see, it is actually integration of differentiation of t is 1, and then we need to integrate this e power t. So anyway, you get the same thing, right? So I'm just taking it like this, e to the power of t itself, right? Then plus what you call this c. Now see, we want actually the solution of equation 1. Therefore, the solution of equation 1 is, in place of u, you can substitute this. Tan y is equals to, tan y into this, e to the power of x square is equals to 1 by 2 into what it is, c, t. What it is, t, actually it is x square. I'm writing value of t also, x square into e to the power of x square minus e to the power of x square plus, this integrating constant c. So like this, you can just find out the solution of this differential equation. Okay, and still, if anyone of you have any questions, you can just raise your hand. We can discuss about this. Yeah, somebody is asking me, can we take e power t as common? Yes, definitely. See, you can take e power x square common from the last term, right? From the last step, the first term in the right hand side. You can take e power x square common, but you cannot cancel it, right? You cannot cancel it because you have a c here, right? If you want to cancel it, you will get c into e power minus x square. Okay, so taking common is not a problem, but you won't get any advantage with that. Okay, so this is about Bernoulli's differential equation. I have one more question, but we discuss this later in the tutorial classes. Now, let me also discuss about this exact type differential equations. Right, look at this. We had seen now variable separable method, linear type differential equations, and then some non-linear type differential equations also. Now there is one more type differential equations for which we can find the solution, which is exact type differential equations. Now see, when we call one differential equation as exact, look at it this way. We are always taking the differential equation as this: dy by dx is equals to some function of x comma y. Right? See, on this right hand side, instead of a single function of x comma y, it may be a rational function of this kind, some function of x comma y divided by some other function of x comma y. Right? When you have it this way, we can just rewrite it in a linear way. You see, if you take what you call a kind of cross multiplication, you will get it something like this: g into dy is equals to f into dx. Right? If you can take cross multiplication, that's how instead of f and g, if you take them as something like m and n, right, we get again a first order ordinary differential equation like this. Right? The same kind of differential equation, but we are just writing it in another way. So even this also represents, m dx plus n dy is equal to 0 also represents a linear differential, a differential equation of first order. Right? It is also a differential equation of first order. Now, when you are given a differential equation of first order like this, we can call this differential equation as an exact differential equation. We can call it as an exact differential equation whenever it satisfies this condition. Right? See here, both m and n are functions of x and y. Now see, when you have those two functions, look at it carefully. M is the coefficient of dx, n is the coefficient of dy. When you are given such a differential equation, we just differentiate m with respect to y partially and then n with respect to x. And in a case, if these two partial derivatives are equal, We call such a differential equation as exact type differential equation, right? So it is an exact type differential equation. Remember, these two may not be equal every time. Whenever these two are equal, then only we are calling it as exact differential equation, right? And when the differential equation is exact, right? You have already verified, understand? You have already verified, and this condition is got satisfied, and you understand this as what you call an exact differential equation. When it is an exact differential equation, you see here, this is the way to write the solution of this differential equation, right? See, you have identified both m as well as n. After identifying m and n, we just integrate this m with respect to x by treating y as a constant. While writing the solution, see, while writing the solution, you integrate both m and n. But see, while integrating m, we integrate it with respect to x, and and we take y as a constant. And then in the second term, you see, while integrating n, we integrate this with respect to y, but see, out of all the terms in n, we consider only the terms which have no x, which have no x, right? I mean, we simply ignore the terms which contain x. There may be several terms in n. There may be several terms in n, right? But we consider only the terms which have no x, right? The terms not containing x. And you may ask me, what if every term has x? We take all this as 0 then. In a case, if all the terms in n have x, then we simply take all this integral as 0, right? So we just consider whenever the differential equation looks like this, we first verify whether it is exact or not. To verify that, we use this condition, whether dou m by dou y is equals to dou n by dou x or not. In case if these two are equal, then see, we proceed with this simple idea to verify, to calculate the solution of this exact type differential equation. It is integration of m dx by taking y as a constant, and integration of non-x terms in n with respect to y. Am I audible now? Is that okay? Somebody is saying the voice is low. There is some fluctuation here. I don't think so. How it is? Yeah. See, for convenience, I'm just writing one simple equation here. See, for example, if you have a differential equation of this kind, 2x square plus y square, 2x square plus y square into dx plus something like, x cube plus y into dy is equals to 0. Right? I'm just taking some functions randomly for m and n. See, the coefficient of dx is m, and the coefficient of dy, it is n. Right? Now see, I'm not verifying whether it is exact or not, but in case if it is exact, I'm just trying to tell you how we are going to integrate them, how we are going to write the solution. Right? Consider this is exact. In case if this is exact, right, we are going to consider m, we are going to integrate m with respect to x, but we are treating this y as a constant. We are just integrating all this with respect to x by treating this y as a constant. Right? When this y is a constant, what happens to this integration? Anybody? You can just recall yourselves. You can write these two aside. Then integration of x square is x cubed by 3. Plus, here this y square is a constant, you see. When y square is a constant, its integration is simply y square multiplied by x. Like when we integrate 2, we write it as 2x. In a similar way, when we integrate this y square, we'll get it as y square into x. Correct? Now, this is about the first term in the given differential equation. Then coming to the second one, you see, we need to take terms independent of x. What do you mean by that? Look at this. Now this is n, x cube plus y. But see, while writing the solution, we take only the terms which have no x. Now see here, there are two terms. One is x cube and the second one is y. In x cube, clearly there is an x. And in the second term, there is no y, there is no x, you see. We consider only the term and we integrate it with respect to y. Right? What if this is xy by chance? Now in both the terms you have x, right? Then in that case, see, there are no terms which have no x. That's how we take all this as simply a 0. The integral value is also 0 here in this case, right? So like that, while writing the solution for an exact type differential equation, we take m and n, we integrate m with respect to x by taking y as a constant, and we integrate n with respect to y by considering only the terms which have no x, right? So that's a way to write the solution in the case of exact type differential equations. But before writing the solution, we need to verify this condition. We need to check whether the given differential equation is exact or not. Okay, so let's see this by taking a simple example. Look at this problem. Now see, as I told you, the question is similar to m dx plus n dy is equals to 0. Right? Keeping that in view, I'm just writing what are m and n. Let m is equal to, see, I'm taking the coefficient of dx as m. So it is 2xy plus y minus tan y. It is m. Then n. See, n is the coefficient of dy. So then it is x square minus x tan square y plus secant square y. Right? So we got both m as well as n. I need to now verify whether this differential equation is exact or not. So to check that, I'm just differentiating m with respect to y. Right? See how much it is. I'm just performing what you call partial differentiation. Now see, while differentiating, m with respect to y, right? As you know, we treat x as a constant, correct? So I'm just keeping this 2x aside, and the y remains here. Differentiation of y is 1 plus differentiation of this y is again 1, then minus, when you differentiate this, what you get here, you see, differentiation of tan y is secant square y. All right. Then see what happens here. Let's keep this aside. Now let me differentiate n with respect to x partially. Now see, when you differentiate n with respect to x, see, first you have x square, so its derivative is 2x. Then minus, see here, you are differentiating it with respect to x, so this tan square y is a constant, correct? So I'm just writing the tan square y as it is, and then what remains here is x. So when we differentiate that x, it is simply 1. And here it is secant square y, when you are differentiated with respect to x, all this y is a constant. So even secant square y is also constant, so its differentiation is 0. But see, are these two same? We can proceed further whenever these two are equal. Whenever dou m by dou y and dou n by dou x are equal, then only we can proceed further. But are these two equal? We can just see that. As we know, secant square y minus tan square y is equals to 1. Isn't it? Secant square y minus tan square y is equals to 1. So how can we write this dou n by dou x? Here you have only tan square y. So then we can write tan square y as secant square y minus 1. Isn't it? We can just exchange these two terms. So keeping this in view, I'm just rewriting this dou n by dou x. So it is 2x minus of, in place of tan square y, I'm writing it this way, secant square y minus 1. So therefore, we can write it as 2x minus secant square y. Then see, minus of this minus, it is plus 1. Now you see clearly, both are equal, dou m by dou y and dou n by dou x. They are same. So therefore, I'm just writing a conclusion at this moment. Dou m by dou y is equals to dou n by dou x. As these two are equal, we can just conclude here, up to here, we can conclude the given differential equation is exact. So therefore, the given differential equation is exact. Now, when the differential equation is exact, the solution, as we discussed till now, we write the solution is, see, it is integration of m dx, and here we are taking y as a constant. Right? We are taking y as a constant. By taking y as a constant, we are going to integrate m with respect to x. Plus, we are going to integrate n with respect to y, but we are considering only non-x terms. Right? The terms which have no x. Right? And this is equals to an integrating constant c. Now see, from here, this implies I'm substituting everything into this. I'm just writing all this y. So what you get here, you see, integration of 2xy plus y minus tan y. We are integrating all this with respect to x by treating y as a constant. Then plus in the next term, you see, we need to consider only non-x terms in n. See, n has actually 3 terms, right? X square root this, and then lastly secant square y. Out of these 3 terms, in the first 2 terms you can see one x. In fact, in the first term it is completely x square. So this is not a non-x term. And here is also there is an x, x multiplied by this. So we simply ignore the first 2 terms, but we consider only the last term, it is exclusively a function of y only. So here we take only that term, secant square y, and we integrate it with respect to y. And then this implies, you see here, you are integrating this by taking y as a constant. So here 2y is also a constant. You can just write it aside. And the remaining here is x. So when we integrate x, it is x square by 2. Plus, here y is a constant, correct? So when we integrate y, it is yx. Minus, the same way, tan y is also a constant. When y is a constant, tan y is also a constant. So when we integrate tan y, it is also x into tan y. Right? Tan y multiplied by x. Plus, when we integrate secant square y, you see, it is again tan y is equals to some c. Right? That's it. You see, I'm just simplifying this. You can just cancel this 2 and we get it like this. X square y plus xy minus, can we take tan y common from these 2? When we take tan y common from them, we'll get it as 1 minus x into tan y is equals to c. So this is the solution of that differential equation. Right? So if anybody have any questions in this, you can unmute yourselves. I mean, you can raise your hand. Or you can use chat box. Right? It's 2:58 almost, and please allow me to explain one more problem so that we can conclude this topic as well. Right? I'll finish it in less than 10 minutes. Please bear me for another 10 minutes. Right? See, if you look at this differential equation, it is also very much similar to m dx plus n dy is equals to 0. So I'm just taking it this way. The coefficient of dx, I'm writing it as m. So m is 2x square plus 6xy minus y square. And then n is the coefficient of dy. See, it is 3x square minus 2xy plus y square. Now I'm just verifying whether this differential equation is exact or not. So you see, I'm just evaluating this dou m by dou y. See, then what happens to this dou m by dou y? See, 2x square is a constant, so its differentiation is 0. Then in 6xy, 6x is a constant as we are differentiating it with respect to y. So when you differentiate that remaining y, it is simply 1, I'm not writing, minus when we differentiate y square, it is 2y. Then dou n by dou x is equals to, see here it is 3x square. So when you differentiate that, 2 times 3x or else 3 times 2x, it is 6x minus, now this is 2y is a constant here. So when you differentiate the remaining x, it is 1 plus, the last term, y square, it is independent of x. So its differentiation is 0. See, you are getting the same. Therefore, at this moment, you can say dou m by dou y is equals to dou n by dou x. As these two are equal, therefore, you can say the given equation is exact. Right? When the given equation is exact, we have a specific procedure to find out the solution. Right? So what it is? Therefore, the solution is, I'm writing it this way, integration of m into dx plus, here you are taking y as a constant, plus integration of n into dy, and while taking n, you are only considering non-x terms. Right? And all this is equals to what you call an integrating constant c. And then see from this, what is m? You are writing all this. It is integration of 2x square plus 6xy minus y square into dx plus integration of, see, in n, you need to take only non-x terms. See, again the same way. In the first term, here is an x. In the second term also, you can find an x. But in the third term, there is no x, right? so that you are considering only one term, the third term, which is y square dy is equals to c. So this implies you can now see integration of 2x square, keeping 2 aside, integration of x square is x cube by 3. Then plus, if you keep this 6y, it is a constant, 6y aside. Uh, when you integrate the remaining x, it is x square by 2. Minus, y square is a constant. So when you integrate that, we get y square into x. Plus, when we integrate y square, it is y cube by 3 is equals to c. Right, I'm just simplifying it again. So it is 2 by 3 x cube plus 6 by 2. It is 3 x square y minus x y square plus y cube by 3 is equals to c. See, this is the solution of this differential equation. Okay, so like this, even when you are given an exact differential equation, just by looking at the given differential equation, we need to first evaluate these two partial derivatives. And when they are equal, we proceed further to write the solution. And what if those two are equal? In case if those two are not equal, I mean, if dou m by dou y and dou n by dou x are not equal, we can say the differential equation is not exact differential equation, right? In fact, there are several methods. There are several methods to find out solutions of those non-exact differential equations. I mean, as we did in the case of non-linear differential equations, when you are given a non-exact differential equation, by making use of several types of integrating factors, we reduce that non-exact differential equation into a what you call an exact differential equation. We reduce the given non-exact differential equation into an exact differential equation. But see, all those methods are not part of our syllabus. So we are just ignoring all of them. We need to only consider these type of differential equations, right? Whenever the given differential equation is exact, then only we can find the solution like this. The other cases, when the differential equation is non-exact, we are not discussing them as part of our syllabus. Okay, so that's one thing. And if you allow me, I'll just explain you this again in a few minutes. What do you say? If you want me to continue for another 2 or 3 minutes, I'll finish up this so that the topic will be completely finished. And then in the next class, we can just continue with the next procedure. The next topic. Okay, thank you. And see, I'm just continuing it this way. It's just like m dx plus n dy is equals to 0. So I'm just writing m and n. Even the problem is little important. Several times it was asked in the examination. See, m is the coefficient of dx here. It is 1 plus e to the power of x by y. And if you write n is the coefficient of dy. It is e to the power of x by y multiplied by 1 minus, this is there next to this, 1 minus x by y. So this is m and this is n. Now see, I'm just trying to verify whether it is exact or not. So to check that, dou m by dou y, see, I'm evaluating this. Dou m by dou y is equals to, see how much it is? You are differentiating all this with respect to y. So differentiation of 1 is 0 plus, look at this carefully. When you differentiate it with respect to y, x is a constant, correct? So when you differentiate an exponential function, we first get this e to the power of x by y as it is. Then we need to differentiate x by y. And while differentiating x by y, we should remember x is a constant. So we first write that x as it is, and the remaining is 1 by y here. When you differentiate that 1 by y, we get minus 1 by y square. Right? See what I've done? I've first differentiated this exponential function. When we differentiate the exponential function, we get that as it is. Then the remaining here is this power x by y. We need to differentiate this x by y. And while differentiating x by y, as we know, x is a constant. See, because you are differentiating it with respect to y, x is a constant. So I've written that as it is. And the remaining is a 1 by y. When we differentiate 1 by y, it is minus 1 by y square. We got everything. So if I write it again here for convenience, it is minus x by y square into e to the power of x by y. Right? That's dou m by dou y. Now see, I'm just writing dou n by dou x also. Now see, let's differentiate this with respect to x. Here you can see you have product of two different functions. One is this exponential function and one more is in the bracket. And both of them have what you call x terms. So we need to differentiate it using what you call UV method, correct? So I'm just proceeding with in this way. I'm taking u as this exponential function. So I'm in the first term, I'm keeping this u as it is, keeping exponential function as it is. If we differentiate, this bracket, when we differentiate this bracket, it is 0 minus, you are differentiating it with respect to x, remember. So 1 by y is a constant, right? Y is a constant or 1 by y is a constant. So the remaining here is only x. When you differentiate that x, it is only 1. So I'm not writing that. See, by keeping this exponential function as it is, I have differentiated the terms in bracket. Plus, now I'm writing this bracket as it is, 1 minus x by y. Now, keeping this as it is, now let us differentiate this exponential function. So as we know, when we differentiate this exponential function, we get it as it is first. Then we need to differentiate what you call x by y. And see here, this time it is differentiation with respect to x. So y is a constant. So you need to write 1 by y as a constant aside, and the remaining here is only this x. So when we differentiate x, it is only 1. So as it is only 1, I'm not writing that. Let us just try to simplify this. Look at this carefully. The first term here, is simply e power x by y. In fact, minus also. Minus e power x by y into 1 by y. And the same term is there here also. I'm just trying to take, this term common from both. So you'll get it this way. E power x by y into 1 by y. If you take this common, see here from the first term, from this term, from this we get only a minus 1. Correct? Then plus, when you took all this common, the remaining is this 1 minus x by y. See, this one can be cancelled, and if you can multiply these two, see what you get here. It is minus x by y into this is 1 by y. So it is minus x by y square into e to the power of x by y. See, you got them as same, right? Dou m by dou y and dou n by dou x, both are same. So therefore, dou m by dou y is equals to dou n by dou x. As these two are equal, we can then say, if I take this as equation 1, or else the given differential equation is exact, right? So when the given differential equation is exact, we need to write the solution like this. Therefore, the solution is integration of, we need to write all this m. So it is 1 plus e to the power of x by y dx. And here we need to treat y as a constant. Then plus, is there any term in n without x? In fact, you see, you have exactly one term in x, though they are in product, you see. All this is one function, or else even if you want to separate them, e power x by y into 1 minus e power x by y into x by y. If you want to write it as two different terms, even then also you can see x in both the terms. So there are no terms without x. So that here you see, we get it as simply 0 into dy is equals to c. So this implies, see, I'm just integrating all these two terms. When you integrate one, it is x plus, when we integrate this, you see, understand it this way, y is a constant. When y is a constant, 1 by y is also a constant. If I take 1 by y is equal to some capital A, what happens to this, you see, it is e to the power of ax. Right? It is now simply e to the power of ax. When we integrate e to the power of ax, what we get? It is e power ax divided by capital A. Correct? So the same thing, I'm just doing it here. E to the power of, when it is x by y, we first get x by y as it is. In the denominator, we get the coefficient of x, which is 1 by y. Right? Similar to this a. So here in the denominator, we get it as 1 by y is equals to c, right? That's it. Then I'm just writing it again. This implies x plus, you can take this 1 by y to the numerator. So it becomes y multiplied by e to the power of x by y is equals to c. That's the solution of this differential equation. Though it looks very complex, when we really try this, it's very easy to solve it. Right? So like this, we can solve what we call exact type differential equations. Okay? So this is what I just want to tell you for today. And if